Hello everyone, I'm really here to present you the subject of my work, which is the development of new generation of sensor design magnetic junction. First of all, I'd like to do a very short introduction of magnetic sensors. So we all know that there are very wide range of applications science. There are many but there are many orders and mainly because they offer complementary. They are cheap and they also payments. And so the objective of this work is basically to develop a new generation of magnetic sensors with comparable performances, but with nanoscale and fully compatible with CMOS integration. So this sensor is basically based on STT-MRAM. This stands for and these are all being developed for Nicolas, mainly because they have several advantages over nanometric technologies. And to create such a device, you basically do two serial layers and then sandwich them with the two. And so you have the same layer and to do this at the end you have two stages. You have the panel and then you have the end panel where the resistivity will and so this is why they are very interesting for binary storage. But here we are more interested in using them as a magnetic sensing unit. So you can see that to switch between the two states, you basically just have to set the current to the so that's very nice, but then where the sensing part? Well, the answer is here. So you can see that there is energy gap between the two states, and you have to bring this energy through certain physical phenomena. And usually what we do is we apply a current. So basically we switch the junction through the STT effect. But we can also switch the junction using an XMR magnetic. And then there's also the possibility that the two effects will combine and switch between the two states. So you can see on the right image, there is the phase diagram of a solar junction that we have been using. And if you move exclusively horizontally, you are basically switching through the magnetic field, right? If you move vertically, you are switching through the STT effect. And then the two white arrows are actually showing the evolution of the rating voltages. So you can see the two. And the idea of this sensor is basically to track the evolution of these switching voltages, which are directly proportional to the external magnetic field. So that's very nice, but then how do we do this? Well, the signal processing is actually very simple. What we do is we apply a triangular signal and we measure the current through the junction. And when there is a switch of resistance, well, because of Ohm's law, you will have a discontinuity, the current that you are measuring. And then if you have this current to a capacitor, you can basically express this discontinuity. And at this time, the magnetic information is actually stored in the time between these discontinuities. And then using a very simple circuit, we can recreate the PWM signal that we can then filter and then sample using simple AEs. So you can see on the top part of the slide, this is the current that we are measuring, and on the bottom part of the slide, this is the so here you can see what we have been measuring. So in blue is the physics was exactly the same for singular signal, and in yellow this is the output. So you can see that we have discontinuities, and you can see that actually the switching voltage is not very stable. And this is because this is a stochastic process. So what we are actually tracking is the Gaussian distribution of the switching voltage actually creates noise in our sensor. This is the biggest source of noise. And then using the yellow signal, we can then transfer the Prejbeanu signal, as I just explained, and we filter this, and we have a nice DC signal. So here a little bit more about the details. So the functions that we are using are incidence wafers, and then we can access them with two with a DC corner, and then you have an SEM image of the 15 nanometers junction, and on the left part of the slide, there is the stack of the junction that we have been using. So you can see that there's a little more than 3 layers. And then on the bottom part of the slide, there is the circuit that we have been using. So you can see that this is a very complicated. We apply the regular voltage, we measure current, the high pass filter, then the Prejbeanu signal conductor, and then the low pass filter. So that's very nice, but with everything I just explained, we have been able to extract the performance of the junctions, so the and also and we also some AC measurements of XML, and so we show that validated, right? And then I just put some numbers to have an idea of the overall performances, but these are just numbers, so not very interesting. But what's more interesting actually is to look at the overall performances of the sensor. So you can see on the top part of the slide, there is commercial, and bottom part of the slide, sensors with similar. So not many papers, right? And these are all based on standard nanometric junction that actually so you can see overall that for commercial sensors, we still have some issues with the noise. About 100 to 1,000 sensors, we have actually better resolution and actually smaller footprint. So that's very interesting. But we have to keep in mind that everything I just presented was demonstrated with wafers actually fabricated a couple of years ago for magnetic memory applications, and everything else in these tables are actually something you need to fully optimize for setting application. Right? So we have a couple of improvement possibilities, and this actually led me to come to the conclusion. So basically, what we have been able to do is to get 15 nanometers junction used as applications, so fully optimized for sensing applications, and yet we have been able to demonstrate comparable performances with reported junctions, magnetoresistive sensors, and actually smaller diameters. One other major advantage of the sensor that we have presented is the simple and compact electronics. So you have a couple of pairs and amplifiers, a few resistors, capacitors, and that's pretty much. And the biggest increase in this sensor is that actually that it's fully compatible with CMOS technology. So in pretty much every other type of magnetoresistive sensors, the technology are not fully supported by foundries, and in this case, we use basically junction developed for magnetic memory applications, right? So founders and companies are actually very interested in making them CMOS compatible for future integration, right? So this actually means that our sensor will be at some point fully compatible with CMOS integration, as is the case for all sensors since decades. Now, what's next? Well, obviously, there is the optimization of the junctions in order to improve the sensitivity and lower the noise, which is mainly induced by the stochasticity of the junction. So we still have a few more months to work on the subject, and then there is also the electronic optimization, so mainly reducing the power consumption, and at the end, the ideal case would be to have a fully integrated reading electronics in order to have a very And basically, this is what we have some applications in mainly so as a single sensing unit, so as sensing single sensors, or as a high density array of magnetic sensing units. So you can see on the right image, this is 3x7 junction array that we manufactured, so 500 nanometers in diameter and about 1 micrometer each sensing unit. And this is actually not ideal, but in the future we are predicting that 20 nanometers junctions are actually feasible. So at the moment we don't have a good yield, but this is technologically feasible, and then the pitch of 1 micrometer could be reduced to maybe 100 nanometers. So we would have very high density arrays for diverse applications in biology, or physics applications, magnetic tracking, magnetic cameras, and so with this, I would like to end this talk to thank you for your attention and thank you for